So for the first one here, we've got 8 to the power of 4. So you actually have to do 8 times 8 times 8 times 8, which is what, 4,096? Now when we have the variables, x to the 5th to the power of 4, what do we do with the powers? Don't add them, we multiply them. A power of a power we multiply. So 5 times 4 is 20. Y to the, you're thinking if you multiply the variables, you add the powers. When it's a power of a power, you multiply the powers.
Yeah, I was thinking that today.
That's right. Yeah. So y to the 7th to the 4th is 28. Now this is z to the 1 to the 4th. Z to the 4. Once we do these other two, we'll come back and do one more example of that with the powers. No, it's the power that it's acting on. What that's saying is you have y to the 7th to the 4th power is y to the 7th times y to the 7th times y to the 7th times y to the 7th. So 7, 14, 21, 28. Our roots, we take the root of the number. What's the square root of 64? Careful. 8. And then it's a square root. Now remember, we don't write it in here, but what's the implied index here? It's a 2. So you divide the powers by 2. So it's going to be x to the 6th, y to the 4. Okay. Something like this, 3x minus 7 squared, that's 3x minus 7 times 3x minus 7. So you've got 9x squared, negative 21x, another negative 21x, and negative 7 times negative 7 is a positive 49. And you just combine your pieces. 9x squared doesn't have anything to combine with. We've got the negative 21x, and another negative 21x makes negative 42x, and a positive 49. When you have a perfect square like that, they actually call this a perfect square trinomial here. It's just a binomial, a two-digit number that's been squared. The first digit here is just this first digit squared. The last digit here is just this last digit squared. Negative 7 squared is 49. The middle digit, as you can see, is the combination of those two. So if I multiply those two, the 3x times negative 7 is negative 21, and I double it, I get negative 42. I'm just throwing that out there in case some of you have seen it before to remind you of it. I don't expect you to memorize that. You can always just multiply it out the long way like I just did here. But there are a lot of shortcuts for stuff. There's patterns. You know, I've mentioned before, you see me doing some calculations pretty quickly. It's because there's patterns in math. And that's one of those patterns is when you square a two-digit algebraic number, the pieces will always fit that pattern. You can put it together quickly that way if you want to. Let's look more at problems like those first two. So let's say we have 5 x to the 8th, y to the 13th, z to the 5th. And we're going to take that to the power of 6. Now the number is raised to the power of 6. 5 to the power of 6 is 5 times 5 times 5 times 5 times 5 times 5. Otherwise known as what, 15,625? Okay. The variables, x to the 8th to the power of 6. Remember, that's going to be 6x to the 8th. So 6 of those sets of 8. So how many x's would there be? Well, 8 times 6 or 48. So that's x to the 48. And then y to the 13 times 6, 78. And then, of course, z to the 30. How are those treating you? Are those okay? Really, the hardest part of those is applying the power to the number.
What's the other way that you add the
Add the powers?
Yeah. No. Wasn't the one that
when I'm multiplying like that, that's where I'd add the powers. So I'd multiply 8 times 11 is 88.
Oh, I know all that.
Yeah, x to the 8th, x to the 5th is x to the 13th. That's where you'd add the powers when you're multiplying.
I thought there was one that was similar to the top one.
Where you add the powers?
Yeah.
Nope, not that. Not that I can think of right now, no. Well, it depends.
I believe you.
Okay. So you run into something like this. That square root again, just like the powers, we apply it separately to each piece. What's the square root of 25? 5. Come on. Square root of x to the 8th? X to the 4. Square root of y to the 18th? Y to the 9. Square root of z squared? Z to the 1 or just z? Did I show you guys that a square root and a power of 1/2 are the same? Okay, we did go through that. And that's exactly why those powers are divided by 1/2 or divided by 2. It's because you're taking x to the 8th. The square root of x to the 8th is really x to the 8th to the power 1/2. 1/2. So you're doing 8 times 1/2, you get the 4. If it's not a square root, it's a cubed root, you may have 64, x to the 21, y to the 15th, z to the 30th. You have to be able to do the third root or the cubed root of 64. You guys remember how to do that on your calculator? A lot of your calculators actually have a third root key. For others of you, it'll be an x root, or sometimes just a box there in front of the root instead of the x or n. So you'd have to put 3, press that key, and then type in 64. So what do you get? Yeah, you've actually got the third root key on there. Yeah. Oh, you do? Okay. So what is the third root of 64? Careful. 4. There you go. You did 64 divided by 3. Did you do 64 yx or caret 1/3? There you go. Yeah. So you got 4 for 64, the third root of 64. How about the third root of x to the 21? X to the 7. Third root of y to the 15. Y to the 5. And the third root of z to the 30th. 10. Perfect. Or if I throw in the fifth root of negative 243, x to the 35, y to the 20. First of all, can I do the fifth root of a negative number? Yes, it's an odd power, an odd index. If it was an even root, I cannot do an even root of a negative power. So I have to be careful with that. What is it going to be? Negative 3. Very good. The fifth root of a negative 243 is negative 3. X to the 7. 35 divided by 5 is 7. And y to the 4. 20 divided by 5 is 4. Now that we've explored that with polynomials, we kind of used scientific notation to introduce our rules with variables and stuff like that. Let's go back the other way. Let's go back to scientific notation. And what happens if I have 3.2 times x to the 8th to the third power? I take my 3.2 to the third power, and I get 32.768. Take my 10 to the 8th to the third power. What's that going to be? I do 8 times 3 is 24. Just like I do with my variables. So it's just like if that were, 5x or whatever. You did the power on the number. You actually had to apply the power, 3.2 to the 5th power. And then with the name, you have to work with the exponents, the powers. 8 times 3 makes 24. Now, of course, I'm not done over here. What do I still have to do to this? I have to move it over. I can only have one non-zero digit in front of my decimal point. So I have to make that 3.2768. What happens to my power of 10? Gets bigger. Number got smaller, went from 32 down to 3. Power gets bigger, from 24 up to 25. How about 1.2 times 10 to the 13th to the 5th power? Oops. 1.2 to the power of 5. 2.48832. By the way, when you do a power like that, how many decimal places were there here? There was 1, right? K to the power of 5 is going to be 1 times 5 or 5 decimal places. Times 10 to the 65th. 13 times 5 is 65. So in your notes, 9.1 times 10 to the negative 11 to the power of, oh, I'll be nice to you, equals 6. Do that one in your notes. So we start out 9.1 to the power of 6. So 567,869.252 times 10 to the negative 66. Now we've got to adjust this. That decimal point's got to be here. 5.6787 we're going to round it to. We probably would not put out all 9 decimal places there, or 8 decimal places. But what do we have to do to our power? It has to get bigger. The number got smaller. It got way smaller. Power has to get bigger, but it's not just going to be by 1. How do we know how much bigger to make it? 5. It has to be made bigger by 1 for every, it has to change by 1 for every decimal place we change. So we went 1, 2, 3, 4, 5 spots. That gets bigger by 5. Negative 61 or negative 66 plus 5 is negative 61. How many of you had that? Cool. So if we had 2.5 times 10 to the negative 9th to the 4th power. (2.5 to the 4th power) 39,0625 times 10 to the negative 36. And here we're back to one where it only has to move 1 spot. So 3.906 times 10 to the negative 35. Other direction. Square root of 6.25 times 10 to the 14th. Just taking the root of radical of scientific notation or root of scientific notation. So just like with our algebraic numbers, I have to take the square root of the number. I have to take the square root of 6.25. So if you punch that in, square root 6.25 better give you 2.5. Oh, my square root didn't work. There it comes. And there it is, 2.5. What do I do to my power of 10? Well, just like I did with my variables, when I square root, the power is divided by 2. So 10 to the 14th, square root it is 10 to the 7th. If I have the square root of 2.89 times 10 to the negative 12th, I have to square root the number. What is the square root of 2.89? 1.7 times 10. What do I do with the power of 10? Negative 6. I divide by 2. Good. So negative 12 divided by 2 is negative 6. We can have the square root of 5.76 times 10 to the 42. Square root of 5.76. 2.4 times 10 to the 21st. Good. Third root of 1.728 times 10 to the 27th. What is the third root of 1.728? 1.2. Good. Times 10 to the 9th. Good. We're dividing the power by 3 now because it's the third root. A third root of 1.331 times 10 to the negative 42nd power. What is the third root of 1.331? (1.1) times 10 to the negative 42 divided by 3 is negative 14. How about a fifth root of, I gotta figure out how to make this one work. (3.71293) times 10 to the 45th. Well, the fifth root of 3.71293 is 1.3. On your calculator, you'll enter 5. Then you'll have to do fifth root. Yours will be, usually it's above the caret key or the power key. I have to go into a math menu on my calculator to do it. So that's fifth root of 3.71293. Hit enter and I get 1.3. So 1.3 times 10 to the 9th. 45 divided by 5 is 9. What do you think? Good stuff? Okay. Well, the good news is there's not going to be any new homework today. We're going to take our last 18 minutes to do a quiz.